Hey, good morning, everybody in Prague. My name is Kevin Myers, and I'm going to be talking to you today about ISIS and MikroTik. But before I get into that, I want to take just a moment to thank Lorenzo and Ron and everybody at the MikroTik Professionals Conference for giving me a chance to come do this remotely, because I had a bit of a conflict and would love to be in Prague but couldn't make it. But Lorenzo was gracious enough to give me a chance to do this remotely. So thank you, 1,000 times thank you. This is great to be a part of this since we haven't had a MUM or any kind of MikroTik meeting since 2019. I think when I was in Austria for the European MUM. So having it again in Europe and having everybody get together is great. I wish I could be there with you. And I'm going to go into a little bit of background about myself before I get into the ISIS presentation. I've been around the MikroTik space for a while. I think I first started working with MikroTik around 2011 or 2012, somewhere in there, when I was working at a telco and got exposed to it. We used it for MPLS, OSPF, and a bunch of different things. And I was hooked. I loved that it was cost effective. I loved that it was flexible. And I've been in love with MikroTik ever since, like a lot of you that are out there watching this. So my background is mainly network architect in the service provider, enterprise, and data center space, although mostly I focus on service provider. And I spend a lot of time on my blog, stubarea51.net, doing a lot of different R&D things with MikroTik. I'll do performance testing and a variety of different articles to kind of figure out what's going on with MikroTik, how far you can push it, configuration options, and that's at stubarea51.net. And you can also find me on Twitter at stubarea51 on Twitter, or X as it is these days. I still call it Twitter. So let's talk a little bit about the history of ISIS, or intermediate system to intermediate system. So some of you may not be familiar with ISIS if you've only ever been exposed to OSPF or BGP, maybe EIGRP, depending on what kind of network equipment that you've worked on or what your background is. But a lot of network engineers that don't work in the service provider space don't get exposed to ISIS. And if we look back at ISIS and a little bit of the history of it, it comes from a time when there were competing standards for layer 3 protocols. And by that, I mean competitors to TCP/IP, what we use now. And there were routing protocols that were being developed around that. And just as we have in life, there are politics that surround the routing protocols. And so if you go back and kind of read the history of data networking and read what was happening at that time, there were two very different camps in the routing community and the networking community of how to tackle the problem of data networking. And ISIS came out of the ISO, International Standards Organization, and DEC, Digital Equipment Corporation. It was a project that they were working on, and because DEC was going to be using CLNS, which is the layer 3 protocol that ISO was working on, they wanted the routing protocol to be based on that. So that's why, as we look at this here in a little bit at the addressing format, it seems so odd to people that have never been exposed to it, because it is an entirely different kind of layer 3 addressing that's a bit archaic. I don't know of anything else that uses it in modern networking. Maybe some really old mainframes possibly, but ISIS is the only thing I'm aware of that uses it. And so we have to look back in time a little bit to see how that came to be and where that came from. And CLNP, CLNS is the protocol that they were developing, which is connectionless mode network protocol and connectionless mode network service. And again, just a refresher on the term, connectionless and connection-oriented people generally associate with TCP and UDP because they refer to reliable versus non-reliable delivery of data. So connection-oriented is generally reliable delivery with acknowledgements. Connectionless is unreliable delivery, where if you are going to use some kind of acknowledgement mechanism, it may exist at the upper layers and not there in that protocol. And so that is the protocol that they had developed, CNLP, CLNS, which is roughly similar to UDP in the TCP/IP stack. And it was developed around the same time as OSPF, where they were competing standards, and OSPF obviously went with TCP/IP. And so it was a bit of a race to see which protocol was going to take off, and it really ended up being OSPF as far as wide-scale adoption. OSPF was far more widely deployed in enterprise networks, data center networks, and even in a lot of service provider networks until ISIS started to really get legs. And ISIS didn't even have IP until later. And so ISIS added the ability to route IP prefixes for as far as TCP IP later on. And then obviously as IPv6 came around, they added the ability to put IPv6 onto it. And now it's the ISIS that we know today. But originally it was just intended to route CLNS prefixes. And so that's something that tells you a little bit about the origin of the protocol. It also uses the same SPF algorithm as OSPF. So remember, it's a link state protocol, so it's concerning itself with the state of all of the links, the cost of links, the number of links, the type of links, looking at an entire topology map of the network and building that topology map using the SPF algorithm is something that OSPF does, and ISIS does that as well, using the very same algorithm, which comes from a Dutch computer scientist named Dijkstra. And I looked up the pronunciation because I was curious about that, and I'm sure my Dutch is horrible, but that's the mathematician and Dutch computer scientist that developed the algorithm that both of these protocols depend on and use every single day. And we talked about this coming out of the early 90s, and we talked about the fact that ISIS is generally only used with service providers and large data centers and hyperscalers like cloud operators up until now. But in the last 5 years, something has changed that has gotten ISIS to be a lot more popular. And namely, that has to do with overlays. Enterprises have embraced overlays because of the move to the cloud pretty significantly. And what they're finding is in data center networks, ISIS makes a really good underlay if you need to build overlays. And a lot of the automation systems that are coming out of building those overlays across the various vendors have started using ISIS as an underlay. Also, the advent of segment routing, which exists for OSPF and for ISIS, is also a driver that is causing network operators, not just in the service provider space, but even in the enterprise space as well, to use ISIS because SR-MPLS on ISIS is probably one of the better implementations of MPLS. And we'll talk a little bit about segment routing later, so I don't want to get too far into that right now. But mainly to mention that after a long period of time of really only being in the service provider domain, ISIS is enjoying some renewed popularity, and we're starting to see it deployed in a lot more places, and I think we'll continue to see growth in ISIS adoption outside of the traditional service provider area. Let's go through some terms real quick before we get into the comparison of OSPF and ISIS. The first term that we're going to look at is ISO, or International Standards Organization. If you look at routing protocols and RFCs, you're going to be familiar with the IETF. You may not be familiar with the ISO because the IETF has kind of taken over as the governing body of network protocols and standards, but the ISO was involved back when ISIS was developed heavily in bringing that to a running state. And then the IETF later developed an RFC that points back to the ISO's official standard for ISIS. And it was kind of a competition between the two back then as to who was going to be the body that really controlled networking. And IEF, I think, kind of won that battle and has been the standard for a long time. But, it's helpful to look back and see what ISO is, where it came from, and how it's relevant for ISIS. The next term that we're going to look at is CLNP, CLNS. As I mentioned previously, the layer 3 protocol that ISIS uses is called the Connectionless Mode Network Protocol and Connectionless Mode Network Service. And CLNS is the part of that protocol that is actually used in ISIS. And it's an adaptation of that protocol, actually, because it does not run on top of CLNS technically. ISIS has its own layer 3 network identifier that is based on CLNS, but is actually distinctly separate from CLNS. And we'll look at that in a little bit. DIS is the designated IS. This is similar to a designated router in OSPF. It controls all of the LSPs, or the link state PDUs, which is the database of the topology of the routes that it knows about, the links that it knows about, and all of that information. And so, similar to a DR and BDR, the DIS doesn't have a backup, though, like OSPF. There's only one DIS that is elected based on the link priority. It just acts as a control point for all of the routers, and they all compare themselves to the DIS. Something else that is notably different is that OSPF only elects a DR, BDR, and multi-access links like broadcast. In ISIS, it's a little bit different because it's going to elect a DIS on any kind of link, whether it's point-to-point or broadcast. So from a consistency standpoint, ISIS is a little simpler to digest because it's more consistent in its behavior than OSPF. OSPF has a lot more special rules for the different network types, and it makes modifications. And so that's one thing you'll see in ISIS is that it's a little more consistent. The last term that we're going to look at that we already mentioned in talking about the DIS are LSPs, which are link state PDUs. And similar to a link state update in OSPF that contains LSAs, LSPs are the foundation of the ISIS database. That is where you'll find all of the information about a link, its cost, the area number that it's in, the sequence number attached to the LSP, the age of the LSP, and it also will tell you the level of the LSP, whether it's level 1 or level 2. So everything that you need to know about this prefix that is getting carried and the topology that's related to this prefix that is going to be advertised, it's in the database, is all going to be in those LSPs. So that's a very important piece that we'll look at when we get in the lab. Now we're going to get into a comparison of ISIS and OSPF, and we're going to look at some high-level items side by side to see how they differ, how they're similar. And the first place that we're going to look at is the RFCs, so that if you want to read further about these, you can see the RFCs that they're based on. Obviously, OSPF has got separate RFCs for IPv4 and IPv6. ISIS has got a single RFC. If you want to read more about those, definitely go read those RFCs. There's a lot of great information about the guts of each protocol and how it operates. ISIS operates on top of layer 2 because the packets really do directly operate right on top of LLC headers. And OSPF, on the other hand, operates on top of layer 3 because it has its own IP protocol. And so the OSPF packets are encapsulated inside of a layer 3 header. And so it operates on top of layer 3. So a little bit of a difference in the control plane there in how these two function. If you look at the routing ID or the ID for the routing instance in OSPF, it uses a dotted decimal notation that is based on IP. It's not an IP address per se, but the dotted decimal notation is the same as an IPv4 address format. Whereas in ISIS, owing to its CLNS heritage, it has a system ID that we will look at an example of breaking apart how that's formed in a slide here coming up, what that looks like, but it draws its system ID from CLNS. If we compare the hierarchy of OSPF and ISIS, this is where they really start to differ because OSPF has a backbone area and all of the other areas attached to the backbone area, and they can't really attach directly to themselves. You could with a virtual link, but you're not really supposed to cross areas without first going through the backbone. It's a fundamental construct of how OSPF is built. ISIS, on the other hand, does not have that strict of a topology structure. It uses level 1 and level 2 links to move routes and exchange information within an area and between areas. And so in ISIS, it is generally accepted that level 2 functions as the backbone, even though there is no dedicated backbone area inside of ISIS. It could be any number that you want for level 2, but level 2 does have a backbone type function and controls routes between areas, whereas level 1 adjacencies control the routes within an area. And one of the things that is probably most different that I notice between OSPF and ISIS is that in OSPF, your area is defined in the link. So when you go into the network and the link that you are going to be forming an adjacency on, that is where your area information is derived from. In ISIS, the router itself is placed into an area and not the links. And the level of the link and adjacency that you establish with other routers is what determines how routes are propagated between areas. So that's a very fundamental difference between the protocols there of having a router in an area versus having a link in an area. So that's something to kind of wrap your head around when you compare these two protocols. We've already talked from a terminology standpoint in the previous slide about the designated router. And in OSPF, you have a DR/BDR election on broadcast segments. And in ISIS, you have a DIS election of the designated IS, as we talked about when we define that term. And that can happen on a broadcast link or a point-to-point link. And finally, if we look at the SPF table, a lot of differences here between OSPF and ISIS, and far too many to go into in the scope of this presentation. But to hit to some of the highlights, in OSPF, LSAs generally refresh every 30 minutes, and the DR and BDR control adjacencies and the updates to LSAs when you're in a broadcast segment. In a point-to-point segment or other types of segments, you're going to form adjacencies directly, and then they're going to exchange their link state updates with the LSAs directly to each other. And that is how OSPF generally deals with the exchange of its database. ISIS, on the other hand, is going to form full adjacencies with all routers, whereas OSPF, in a broadcast segment, routers only form full adjacencies with the DR and the BDR, and then two-way adjacencies to every other router that is in that LAN segment. And this is one of those things that OSPF is built on that, in my opinion, it comes from a time when routers didn't have a lot of CPU. And so they made all of these different design decisions in OSPF to deal with the fact that routers didn't have very powerful CPUs. Fast forward 30 years later, and routers have far more powerful CPUs. So again, coming back to the consistency of ISIS, even though ISIS forms full adjacencies with every other router, the complexity of what it's doing isn't the same as OSPF. It doesn't have the baggage that OSPF does because it just forms a full adjacency with every other router. So, and that's probably one of the other reasons that you're seeing ISIS rise in popularity is that the mechanics of the protocol are, I don't want to say simple because they're not simple, but they are a little bit more streamlined than OSPF. So again, looking at the LSPs and looking at the SPF table for ISIS, your LSPs refresh every 20 minutes, and then all routers have to compare their LSPs against whoever the designated IS router is in that segment, whether it's two routers on a point-to-point link or it's multiple routers in a broadcast area. There is a concept called a pseudonode, which is this virtual node that the DIS creates, and that is where all of the routers send their LSPs to and compare their LSPs against so that everybody has the same copy of the SPF table in that area. And again, both point-to-point and broadcast links elect the DIS and form an adjacency, and those make up some very fundamental differences between OSPF and ISIS as it relates to the SPF table. So let's look at a few terms before we go into looking at the slide of an ISIS address format overview. And the first one is AFI, which stands for Authority and Format Identifier. And it's important to disambiguate this from AFI that we normally work with, which is the address family indicator for TCP/IP, which would be IPv4, IPv6, things like that. But in this case, this comes out of the CLNS world, and that AFI is a number that we're mainly only concerning ourselves with 49 because that indicates private addressing for CLNS, and that's pretty much the only one that we use for ISIS. Area ID is the next one that we're going to look at, and this is a 3-byte field that is made up of the AFI number as well as the actual area ID itself, which is grouped into a series of octets. And in this case, it is 2 bytes worth, and it's set off by a decimal. And we'll see that in the overview slide that shows the addressing format in the next slide. And it's just like an OSPF. This number is going to identify the area that we're working with in ISIS. System identifier is the next part of the address that we're going to look at. And it functions kind of as a combination of a router ID and also as part of the addressing to uniquely identify the router within the area. And it's very, very common now that we're in an IP world and an IPv6 world to encode the loopback address of your IPv4 address into the system identifier. It makes it a lot easier to see the origin of where it came from, since we're mainly concerned about IP addressing and we only have to deal with this format for ISIS routing protocol. So in the example that we're going to give, we're going to encode 100.127.1.1 into the system ID as 1001.2700.1001. And a lot of people kind of confuse this for IPv6. I think I mentioned this before, but you also can use letters in these fields. So if you don't pay close enough attention, it kind of looks like an IPv6 address at first glance, or it can. And the final term that we're going to go through is selector. And in MikroTik, you're not going to set this. The system will automatically set it when it's building the LSPs. And the closest thing that we can equate it to is that of like a port or a socket. In the way that you're going to configure it in MikroTik, it will always be 0. So it's not even an option that you configure, but it is part of the OSI address overview. Now that we've gone through some terms, we're going to take a look at our ISIS net address format. And this is what is going to be assigned to the router in your instance configuration. So if you look at the syntax on the slide here, you can see how this is set in RouterOS version 7 and the breakdown of where we get all these fields. And so this is one of the reasons that we had to go through the long and sometimes boring explanation of all the different terms, because this is how they all fit together. This is what it is all comprised of. And I created this graphic because it was definitely hard for me as I was learning ISIS to understand where this came from, where these fields came from. And so I wanted to put together something that made it clearer as to where these numbers are derived, how they fit in, and what their function is. And so now we see everything together, and you can see the AFI in the very beginning of the address as an integer of 49, indicating private addressing. And that's mainly all we're going to use. There's no reason to use anything else because we're not routing CLNS, we're routing TCP/IP. So that can always stay as 49. The area ID, in this case, obviously I did Area 51 because my Twitter handle is Stub Area 51, and so is the blog. So I tend to use Area 51 in my IGP topologies. And we've got that encoded in here as well. And you can see that in the blue in the addressing format overview, as well as how it's configured in MikroTik. And in MikroTik, it separates this out into 2 different commands that you're setting. So we're setting the area as 49.0051 under the areas command. And then the system ID, which, if you recall, is the portion that must be unique within an area to the router. And ideally, it's going to be unique across the entire routing domain for ISIS. It has to be unique within an area, but it's best to make it unique across the entire network. And so in this case, to make that easy, we're going to match the IPv4 loopback like we had said. And so if you look at this format and recall what we did, 1001.2700.1001 is actually 100.127.1.1 and is the loopback ID of that router. And that's how we encode it. And you can see that in the system ID setting down below in the purple highlight. And then the last field is the selector, or the net selector, which, if you recall the terms from the previous slide, is not something that we can set because a net address has to be 00 when it's configured. So MikroTik left that off because it needs to be 0. There's not any other value that it's going to be. And if the selector does change, the operating system will actually change it as it's iterating the address in the LSPs. And so there's not anything that you need to do. And that's why we don't see the yellow highlight in the MikroTik configuration below, because the system is going to set that dynamically. Okay, now we've gotten to the fun part where we actually get to get into the lab and we get to see how all of this actually works and how it all fits together. So I want to take a little bit of time to introduce you to the topology and what we put together here in EVE-NG and the network that we're going to be looking at and putting this into. So I try very hard when I do lab topologies to build something that is realistic and real world. And since most of the users that I've put the focus of my work on for MikroTik is WISP and FISP space, you'll see that this is a network architecture that relates to a WISP and FISP or hybrid ISP operator. And you've got a core here with border layers, core layer, aggregation layer, and then you've also got some areas here for WISP and FISP. And so this represents a pretty accurate topology because it shows a little bit of the partial mesh that you would see in a WISP network. And then it shows you might have an isolated fiber network that aggregates into a different router. And although it's a simpler topology than most ISPs for the purposes of labbing, it's still a fairly accurate one to represent the ISP topology. And then one of the other things you'll notice down there is we're going to do a little interop testing with IP Infusion, which is a white box operating system that we commonly use with MikroTik inside ISPs. So we're going to interop with another OS with ISIS, and we're going to see what that looks like a little bit later in the lab series. So just to orient you to the ISIS topology, we talked about different levels, the levels at which ISIS operates to control routes within areas and routes between areas. So if you look in the lab topology here, you'll see that we have level 1 inside of an area here, and this is area 50. And then we have ISIS level 1 here inside of area 52. And then we have area 51 here in the middle, which is a level 2 topology. And so all of those are going to connect together, and we're going to show a connection within just a level 2 adjacency by here shortly by connecting core 1 and ag 1 together. So why don't we go ahead and pop up the terminal and let's go take a look at the syntax. So the first thing that we're going to do is look at the instance. So if you've worked in routing protocols in MikroTik before, then one of the things that you know is that the instance is kind of the construct around which it's built. Whether it's RIP, whether it's BGP, whether it's ISIS, there is an instance that you're going to build that has certain attributes, and ISIS is no different. So if we go in and look at routing, ISIS, and instance, and we're going to add an instance, and we hit tab, we're going to see a variety of options pop up here of things that you can do. And it's going to be pretty similar to OSPF. If you configured OSPF in RouterOS version 7, you're going to see a lot of the same things that are in here. We have AFIs, which allows us to specify either IP, IPv4, or IPv6. And point of note, another disambiguation, this is not the AFI that is in the ISIS addressing, the authority and format identifier. This is the AFI that we know and love, which selects which protocol of IP that you're going to be using. You have areas that can be defined, and we're going to show that as we configure the system instance. And we've got comments and filter chains, and then you're going to see a whole bunch of options that are either prepended by level 1 or level 2, or L1 and L2. And this is something that illustrates how ISIS is put together in the configuration options that you choose, because the router can either operate as level 1, level 2, or level 1 and level 2 on the interfaces. And again, to reiterate a point we made earlier, the router belongs to an area, and then the interfaces belong to levels. Again, it's a different mental shift than OSPF, where interfaces belong to areas. In this case, the router belongs to the area, and we'll see that as we configure the instance here. So if you look through the level 1 and level 2 options, you're going to see similar things in OSPF. We can originate a default. We can select an out filter chain. We can select an in filter chain. We have LSP max age, max size, LSP refresh interval, which is all very common with, if you look at OSPF, the same kind of things that you can do on LSAs, except in here it's broken down into L1 and L2 for ISIS because of the way that it's structured. And we also have default origination, which we'll try here in a little bit, and originate a default out of this instance through redistribution. Then you have standard redistribution by level 1 or level 2 if you want to redistribute static routes, or BGP, or OSPF, or other ISIS. And then finally, you have the name of the instance, you have the system ID, which is something that we alluded to in the definitions that we went through, and then you also have the VRF. So we're going to go through the VRF and configure that. Actually, I take that back. We're not configuring the VRF in this instance, but I wanted to call it out because it's relevant if you're going to be running a provider network and you do need to build it in different VRFs. That's something that has been added in RouterOS version 7. VRF support is really, really good, and it can be added to almost anything now. In fact, I think they recently added it to DNS. So most of the VRF available services are being added, and so it's nice that you're able to put it in there. So let's go into the instance, and let's go ahead and add an instance. So we've already taken out the instance here so that we can add it back in. So I'm going to go copy my config here, and we're going to add in an instance into Core 1. So there is my instance configuration in Core 1. So let's take a look at that and see what that's telling us. And if you look, you can see the AFIs that we've selected are IP and IPv6. Our area ID is 49.0051 that we talked about in our previous slide when we broke down the format. And we gave it a name of IPVX-ISIS-1. And IPVX is kind of my little shorthand code when I'm combining more than one protocol into an instance. So in this case, I have IPv4 and IPv6 running in the same instance. And so I use IPVX, with X being a bit of a variable, to indicate to me as the network operator that I'm combining more than one protocol in. And as a side note, that's something that makes ISIS a lot more flexible in that you can run IPv4 and IPv6 in the same instance. And so that's one of the things that helps to lower the control plane CPU usage when you're putting this out across a really big network versus OSPF, where you've got to run it in separate instances, at least on MikroTik. In other operating systems, I think you can run them together. But in MikroTik, at least, OSPF has to be run in two separate instances for IPv4 and IPv6. And then finally, we have the system ID of 1001, 2700, 1001. And if you recall from our addressing slide, that's actually the loopback address of 100.127.1.1. And then we can see that here if we look at an IP address print. And you can see our loopback address right here, 100.127.1.1, and that is our Core 1 loopback, and we've encoded that into our system ID here using the CLNS format. So now let's go ahead and add our second instance. We're going to connect Core 1 over to AG1 in level 2 adjacency. So these two right here, we're going to connect together. So now we're going to flip over to AG1. And we're going to do the very same thing. We're going to add the instance configuration in to AG1. And we're going to paste that in. And if you look at that, we have similar things, IPv4 and IPv6. We have an area of 49.0051. And we have IPVX ISIS1 like we did in the other one, but a slightly different system ID because, again, remember that has to be unique within an area, and functionally it has to be unique across the entire network. So in this case, we have 100.127.1.21, which is our AG router. And so that's the loopback of our AG router. And so if you go look at the AG router, and we look here, then you're going to notice that that is the loopback address here. So we've matched that into our system ID in both places. Now, if we go look and see routing, ISIS, neighbor, print, do we have a neighbor? And we don't. And the reason we don't have a neighbor is we haven't added any interfaces and levels yet. So that is the next thing that we're going to look at doing. And here we can go and look, see routing ISIS, neighbor, print, and we don't have any neighbors over here. So that's the next thing that we've got to go add in is we've got to get our interface templates and define our interfaces just like OSPF. If you've worked on OSPF in RouterOS version 7, you're going to be familiar with interface templates because OSPF uses them in very much the same way. So we're going to go get our interface templates and we're going to go paste that in so that we have these in here. And then we'll go into interface templates and options in a little bit more detail, but we'll take a brief overview look at these. And so if we look at our first router in the core, we're going to paste that in. And here's what that looks like. And so it's a little hard to see because I've got the font bigger to make it easier for you to see it, but those are all in there now. So let's do routing ISIS interface template export. And now we can see that we have our interface templates in here. So you can see that we've got both of our loopbacks in here at level 2 because we're in the core node here. We haven't crossed into a level 1 adjacency. And we have all the Ethernet interfaces that are in our EVE-NG topology. And we've also got an LACP interface. So just like OSPF, if you have a logical construct for an interface that is what you're going to put layer 3 on, that's what you're going to put into ISIS as well, just like OSPF. So now we need to go in and paste the interfaces into AG1, and let's see if we can get an ISIS neighbor. So we're going to go ahead and copy that and paste that in. And now we have that in. So let's do an export. And we can see the same thing. One of the things that you'll notice that is a little bit different here is that in this link here, Ether4, which is leading off to the WISP network up above, where you can see in the purple lines, we've got an L1, L2 adjacency because we're trying to establish an L1, L2 adjacency out of that down into the WISP network. And so we'll talk about that briefly, what that means, but that is the way in ISIS that if two different topologies need to converge through the same routers, meaning if you need a router to function as a backbone router, but also as a router within the area, then you can use the L1, L2 adjacency, and it will maintain two completely different topology tables and adjacency sets in order to do an L1, L2 adjacency. So now we can come back and take a look and see, do we have any neighbors? And now we do. So now you can actually see that we have neighbors up all around us. So we've got other routers that were already pre-configured in the topology, and we've got these two routers that we just configured. So we've got 4 ISIS neighbors, and you can see the interfaces that they're here on. Ether 6, Ether 4, bonding 0, and so on and so forth. So let's go into our other router and see routing ISIS neighbor print. And the same is true. We have neighbors going all around us, and you can see the source ID aligns with the neighbor that it's coming from. And so this is where our encoding of our loopback address becomes really helpful because we can generally see what router this came from. So now let's take a look at our interface options. And we looked at our interface template options. We pasted them in kind of quickly, but let's just take a look at what options we have here and what we can set. So if you look at the tab complete here, we have broadcast options, we have point-to-point options. And if we dive into the broadcast options just a little bit, you can see there's a whole bunch of them. So we have 2 basic types of network types in ISIS. We've got broadcast and we have point-to-point. And then just like OSPF, there's all kinds of things we can set here. Hello interval, hello multiplier, the metric, priority, other intervals. And the same is true for broadcast in L2. You see L1 over there on the left side. And then as you go to the middle and the right side, you see level 2. And you can set the same values there. So if we back up and look at the general options, then you've also got levels that you can set. We can set level 1. We can set level 2, and we can also set level 1 and level 2, and that's done by the interface level. And then it's also got an instance reference so that if you are running more than one instance, then you can specify that instance and tie that all together. But now we're going to move on to doing a quick redistribution exercise, and we're going to redistribute a default into the network. And for this, we're going to move over to our edge router, which is there in the upper left. And we're going to take a look at our routing ISIS instance, and we're going to export it. And so we have an instance running in area 51, and it is good to go. We have neighbors, I believe. We'll check that. So if we go routing ISIS neighbor print rather, then you can see that we have neighbors and that it knows about the rest of the topology and the way it's connected to the core and the other border. So what we're going to do is just modify the instance, and we're going to do a very simple redistribution and originate a default, which is a special type of redistribution, just like it is in OSPF. So if we take that config, I'm going to copy my config here and then paste that in, and let's set that for originate always. So you can do if installed or never. If installed is my preference in an operational network, because if the default route gets withdrawn, then it'll get withdrawn in this redistribution. But to make things simple, we're going to use always, which will always turn it on. In production, be careful with this because it can lead to routing loops. So we're going to go ahead and set that. It's going to ask us what instance number we have. And if we look up there, we only have one instance. So it's going to be instance number 0. And now that we've set that, let's come over to another router. And let's look at our ag router, and let's go into routing route. And if you're not familiar with routing route is the routing database that is common to all routes across RouterOS, regardless of protocol. And it's kind of my new favorite thing in RouterOS version 7 because it makes it very easy to see where things are coming from. So I'm going to do a print where ISIS and my destination address equals my default route. So I'm going to combine a couple operators in here. And there we go. We've got a default route coming in from ISIS. You can see the I there as ISIS. And the distance of 115 also lets you know that it's ISIS. But let's also check IPv6 because we have it in IPv6. So if I go look at ::0, get my IPv6 right, then we also have an IPv6 default route. But you'll notice, as I mentioned before, it's unreachable because I don't think IPv6 is finished. So I wanted to show you that we do have both types of defaults that are injected here. And this is several hops into the network. This is 2 hops away from the border. But it's not quite working yet. So I'm sure we'll see that soon in new releases that we'll get IPv6 working and we can play around with that as well. So now we're going to move over to take a look at our core router, and let's just take a look at redistribution of other protocols. So if we look at ISIS instance and we look at set options, we look at redistribute, and let's do an L2 redistribute because we're in an L2 level 2 section here. And if we look at level 2 redistribute, we have a lot of options here of protocols. We have BGP, MPLS VPN, which is be your L3 VPN, connected routes, routes from DHCP, fantasy routes, which is MikroTik's routing generator, modem routes, which is going to be your LTE 5G stuff. And then obviously we've got OSPF, static, RIP, and then also VPN. So if you're running something like Zero Tier or WireGuard and you've got routes injected from the VPN, then you can dump those into ISIS as well, just like BGP. So that's really nice. And not terribly shocking, just like any other routing protocol, you can redistribute any other routing protocol that is on there. And for brevity, we're going to skip actually doing it, but I wanted to show you that these are there. So now let's move on to some validation commands. We've already looked at a few of these, but we've got the routing route print that we looked at. So we're going to dive into that again just for a minute and take a look at that. So we'll move back over here since we just ran that command. And let's take a look at all the routes that are ISI. So now we're looking at routing route print where ISIS and tab complete. And now you can see all of the ISIS routes. Now, if I wanted to look at all the IPv4 routes, then I could filter it further and say, let's do and AFI equals IP4. And this is where the address family gets a little bit weird because in the routing route database, it's IP4 and IP6, but in the instances, it's IP and IPv6. So watch out for that. It's a little bit of a difference in the syntax and the way that it works. But I can see all of the ISIS routes across the entire network through here. And then I can also do the same thing with IPv6. And I can see, obviously, they're unreachable. As we said, IPv6 is a work in progress, but at least they're there. And we can see those propagating in as well. So routing route is a very, very powerful way, not just for ISIS, but for any routing protocol to look at the most detailed view of a route before it gets sent off to other databases and the actual routing tables, which are your IP route print and IPv6 route print, respectively. Now that we've looked at that, let's look at our routing ISIS neighbor print. You've seen me do this before, but let's just take a look and print details so we can see what information is there. And you'll notice, as we looked before, you're going to have the instance that's there, so you can see what neighbors are up, the interface that it's coming in on, the level type that's associated with it, and you're also going to have something called the SNPA, which is, in the world of ISIS and the OSI addressing model, it uses the MAC address as a layer 2 mechanism to provide reachability. And so that's what that's doing, and it just takes the MAC address of the interface and slots it in there, even though it's a construct of the CLNS and OSI addressing family. And then we can also see the source ID that shows what router that is coming from, what's the source ID of the router that we have an adjacency with, and that the state is up. So a lot of information in here that you can look at to see what's going on with your ISIS neighbors. And then finally, something that we haven't run yet is we're going to look at the LSPs. And if you recall, in our terms and definitions, LSP is link state PDU, sometimes seen it referred to as link state packet. And we're going to look at routing ISIS LSP print. And this is everything. This shows you everything that ISIS knows about. And if you've ever run this in OSPF and you're looking at the LSA database, it's got a very similar structure and feel because it's a link state database. And link state databases tend to be formatted in a very similar way. So if we look at this, it shows us the instance that it came from, the level it's at, our LSP ID, and we also get things like the age of the LSP, which if you remember is 20 minutes, and then it decrements down from there, or 1200 seconds. A checksum to make sure that we've got the right piece of data, and a sequence number. And then the body of it, just like OSPF, is going to show you the information about the routes. Reachability, it shows you what intermediate systems are reachable over the ISIS CLNS style addressing, and it also shows you IP reachability. And as we scroll down further, we can see IPv6 reachability as well. So all of that gets encoded into an LSP, similar to an LSA in OSPF, and then I won't go through all of these, but you can go through all of the LSPs that are there and see the entire database of what's going on. So finally, the last thing that I want to show you before we wrap up is just a little bit of interop with another operating system. So as I come back over here to the lab, I'm going to take my window capture off here just for a second so you can see the router that is down here at the bottom with the IP Infusion logo. And the reason I chose IP Infusion is that we often pair IP Infusion and MikroTik together in production networks. It's very, very popular. You see it being used a lot because they both solve different problems. And MikroTik is great, but sometimes if we need 400 gig or a big peering router, we'll use IP Infusion and pair it together with MikroTik. So I thought IP Infusion was a perfect choice to mesh together with MikroTik to show what interop looks like for ISIS. So we're going to come back to our window over here and come back to our terminal, and then we're going to flip over to our OCNOS router. And we'll get into that. And you'll notice that it's a Cisco style CLI or an industry standard CLI, if you're being specific. And we'll just take a quick look at our running config for ISIS. And you'll notice, similar to Cisco, it has a router definition that's similar to Cisco. We have our net defined in Area 51, just like our MikroTik. And then we've configured an interface to be level 2, and that it's tied to this ISIS instance. So very similar to MikroTik, just slightly different syntax. And let's go take a look and see if we have routes. And we're going to do a show IP route, ISIS. And we do. We have all the routes that are coming out of the MikroTik network there, coming into the IP Infusion router. And we can see all those routes coming in at level 2. And if we go look at the database, and we look at the show router ISIS, we can look at the database, and then we'll see same kind of thing that we saw with the LSPs. You can see all of the LSPs and all the information about the link state database for ISIS here. That's all coming in from the MikroTik network. And we can also look at the topology, and we can see neighbors and other routers that this router knows about. So if we look at taking one of those and we look at one of our IDs here, or one of our loopback addresses, we can test reachability, and we can do 100.127.1.1, and there we go. And we've got reachability out of this router into the MikroTik network over ISIS, as we'd expect. And one of the interesting things, I told you we get back to segment routing. It's the last thing I'll finish with. You'll notice as you look at the ISIS commands in here that you do have segment routing options in this operating system because it does support segment routing with ISIS and things like TILFA, which is topology independent loop free alternate. And so what's cool about ISIS, and OSPF does the same thing, is that if you're running segment routing, a traditional ISIS network that is not running segment routing can still exchange routes because at the core of segment routing, it's still just an IGP with some extra types thrown in there so that it works with legacy OSPF or ISIS into a segment routing network. And so it makes it easy to exchange routes. And so if we were to turn on segment routing, and maybe this is something I'll do in a new lab, we would see that we would still have reachability between the MikroTik network and this network as it enters the labeled segment routing portion of the network. So I just wanted to show you this quick bit of interop. I'll probably do more on it on the blog or another video later. But that wraps up the presentation on ISIS with MikroTik. I hope you enjoyed it. If you made it this far, congratulations. It's a long slog. And if you have questions, comments, clarifications, whatever, feel free to reach out to me at StubArea51 on Twitter or hit me up on LinkedIn. And thanks and enjoy the rest of the conference and have an awesome day.